Vi behöver dricka upp lite.
Okay, we are live. Welcome to the battery webinar. This will be broadcasted from SICK IVP, our machine vision R&D department from Linköping in Sweden. My name is Christian Keskitalo. I'm working as a head of sales, and with me today is...
My name is Sofia Nilsson. I'm working as a product manager, and I will talk about configurable 3D vision today.
And my name is Nils Högberg. I'm a product manager for 3D Vision as well, and I will talk about our new Ranger 3 camera.
My name is Victor Smedby. I'm also product manager, but for smart cameras and AI.
And I'm Håkan Torngren. I will talk about the product portfolio in general and a bit of application overview. I work as business developer here in SICK Linköping. So let's go.
Great, what a team. Let's go. Let's start. Okay, then we are ongoing. Why don't I... Jag kan inte byta blad. Kan inte byta bild. I need some small assistance here to start the PowerPoint. Sorry for that inconvenience. Great, now we're live. Thank you, Victor. Good to have IT specialist here. That's always the thing when you are doing something live. This is the agenda, and I will start with showing you some overview of the SICK company and also what we are already doing in battery industry and especially quality control. After me, Håkan Törngren, the oracle of machine vision, will describe our portfolio and an overview and show some examples from applications. And Victor will talk about configurable 2D and deep learning. We also in this webinar have 3 new launches that we will show you, and you will be the first ones to see that globally. These are products that will be launched next week. So, and this webinar will be also recorded, and you will get the recordings after Tuesday next week. After Victor, Sofia will describe configurable 3D and Surface Plus, and Nils will talk about advanced 3D and 2D combined also. And after this presentation, we will also have a Q&A session. And in the Q&A session, we will answer all your questions. And questions you can already type into the chat function in the WebEx. We will answer all the questions, and if we get additional questions left, we will come back to you later on. So, great. Shortly about SICK then. SICK is a global company. We are located here in Sweden right now, but our headquarters is in Germany, in the southwest corner, close to Freiburg. And SICK is an innovation-driven company. And you will see a few of the innovations today. We have close to 4,000 patents, which is a very shows you the innovation rate we have. If you look where we are present today in battery industry, we have an overview here from mixing all the way to pack assembly. You can find us in all parts of the battery production with all our sensor solutions. From predictive maintenance to security, machine vision safety, we are controlling emissions, and we do really good quality control applications. Why quality control then? Why is quality control needed? There are several reasons for sure. One is to increase the yield, to shorten the ramp-up phase also is important. And you also want to reduce scrap and scrap cost. And by that also, for sure, also raw material and sustainability is important. So production quality has a big impact on battery performance and also safety. How then can quality control solutions help you? What kind of things do you need to consider? One is for sure the increased output and high productivity quality. We need to identify failures in the production as early as possible. And our solution can also help you in different ways. I was talking about output. For sure, increased output is one of and high speed is very important. Increase accuracy, ensure high product quality, and also avoid hazardous solutions during the manufacturing process. And when you are looking for sensor solutions, what do you do when you select? One is accuracy, measurement accuracy. One is measurement speed. If you want higher speed, you need to increase output through improved cycle time. Reliability of solutions based on the high scrap cost and the high impact on product performance. You need robust and proven solutions that's required. And you always have the cost issues for sure. A scalable solution, many of our solutions are scalable. That's very nice to have, because then you can adapt the performance to the application and get the right sensor for the right price. Here we see a short overview over the applications and quality control that we are already into. And you see that there are various amount of them, from electrode mixing all the way until the end in pack assembly. So we are very much present in this. Okay, short overview about SICK gives you an idea of the company and where we are today. By that, I will hand over to the Oracle of Machine Vision, Håkan Thorngren. Welcome.
Thank you for those encouraging words. Pressure is on. Hello, I'm Håkan Thorngren. As Christian mentioned, I will give you a short overview of the entire offering portfolio, as well as some application examples. We start with application examples. One category of applications we are into is 2D and 3D surface inspection. This means, for example, detecting blisters and defects in foiled products. Surface defects in terms of dents or bulges is another example. Scratches on these surfaces, also important to detect. And lastly, contamination, various stains. For example, fingerprints like this picture, or electrolyte stains, or whatever that have come onto the surface. And for this, we use a unique technology of mixing 3D cameras plus multiple lighting in a way that we can acquire a 3D image and images that are specialized for specific surface defect detection, for example, dents and scratches. You see in these images that the signature of the dents and the scratches is highly amplified, thanks to this, the way we arrange the light sources combined with a bit of pre-processing. Next, this is a messy slide, but I hope you will be able to follow me anyway. These are just a bunch of examples where we have been helping out customers over time here. 2D and 3D dimensioning, for example, measuring the dimensions and the height of structures like poles, terminals, etc. Coplanarity of these surfaces, also important. If you increase the scale of it, we can look at XYZ dimensions of modules and packs, more ready-to-go assemblies. Weld inspection is a big topic. The weld seam between the top lid and the case on prism batteries. The caps where you fill electrolyte are sometimes welded. Glue beads are used in the later stages of the process when you are working with modules and packs. Going further upstream the process in the foil manufacturing, positioning, measuring the width, the thickness, even wrinkles on, for example, separator sheets has been topics. Cylinder batteries is something that Victor will exemplify later on with the new Inspector 830 launch, AI-based detection of, for example, scratches on the ends of the batteries. When you assemble a cylinder battery pack, you use terminal plates. Checking the welds on those is another example. If we shift the wavelength a little bit, we are also into thermal inspection, detecting over temperature in the whole chain, basically from cells to modules and packs. And lastly, the entire battery pack that goes into the car, checking that before it's being lifted in its position in the car chassis, detecting foreign objects, somebody left a tool or there is something that should not really be there, is then detected. It can also be used for checking presence of key components like fastening elements, screws, bolts, whatever. So this is a bunch of examples of stuff we have been into over the years. And what we are going in with is essentially this. So this is the overview of the product portfolio. And I'm not going to go into too much details here, but we have a scalability, and this is the key thing concerning our portfolio, that you can start with a smaller level of a solution and scale that up thanks to clever software offerings, etc. Starting with embedded cameras in various price, performance, different resolution, color/monochrome. We got streaming cameras. Accessories is of course important when it comes to lensing, illumination, etc. 3D is the DNA of our site here in Linköping. It started with pioneering the first 3D camera back in the 90s. If I remember correctly, we launched it in 1996. And since then, we have been improving the design and refining it. And today we have 6 different cameras with included laser and lensing in a factory calibrated geometry called Ruler. We have the Ranger, which we would refer to as the Swiss Army knife when it comes to streaming cameras. We got time of flight cameras, we got 3D smart cameras, etc., etc. From software point of view, we have 2 key offerings, and that is the Nova offering, which is running on the embedded cameras as well as on controllers, incorporating both classic image processing, rule-based, as well as deep learning. For the advanced applications, we also offer a stream, which is basically the camera is streaming raw data images, which is then processed in our Stream software toolbox on regular PCs. So here you get maximized performance, but well, it's a little bit higher effort, obviously. So I think that wraps up what I intended to mention and convey in this section. And now I will hand over to Victor Smedby, the guru in 2D imaging.
Well, thank you, Håkan. So, my name is Victor Smedby, as Håkan said, and I'm going to talk about configurable 2D vision and deep learning. And as I mentioned before, I'm a strategic product manager responsible for 2D vision sensors. But before I talk about deep learning, I'm going to talk about a new product. It's a very excited product announcement, and I hope that you will enjoy this video. So sit back. So what you just witnessed was, I would call it the world premiere of this video. It was never shown publicly like this before. It is very exciting for me to show this product, the Inspector 830. We have been working on it for a long time, and it is finally here. This device, with this device, we want to put an end to wasted material, faulty products. We want to put an end to long setup times or expensive reconfigurations when product change. We want to put an end to complicated integration or data trapped on the shop floor. It is high speed, it is high resolution, and this lets you inspect every single part, every detail, every time. With this, we want to make machine vision stress-free. So there are some key aspects of this device. Number one, it is powered by AI. So it's heavily focusing on the AI inspection of machine vision. And specifically, what this means is that you can use examples of items to teach the camera what an item should look like and what it should not look like. I will talk more about this later. It has a quad-core CPU and a special AI accelerator, and this makes it our fastest camera yet. It is really, really high-quality pictures in up to 5.1 megapixels and really excellent integrated illumination. And it will also be launched in a color version. I talked about AI, and there are one important thing to know about our AI offering. It is that we have kind of a double offering for AI. It's a combined offering where we have on one hand what we call AI trained on device. So with this device in the production line, I can collect data, train and execute the inspection directly on the device. I don't need a powerful PC. I don't need any kind of special service or anything like this. It's all running in the device, both training and the inspection afterwards. At the same time, we are offering tools for what we call AI trained with DStudio. So DStudio is our cloud service to make train optimized inspections that increases the accuracy and speed when they're then running on the device. Again, it's running standalone at the production line. But this tool also lets you do things like data management and collaborative annotation. So it's for bigger projects. So you can always start on device, and then when you see that maybe this project is growing bigger than we thought, then you can move into DStudio. And this, we think, is a very powerful aspect of our offering here. Some other aspects with this camera is that it is really good at networking. We have dual port Ethernet IP and dual port Profinet, and we have gigabit Ethernet for image and data logging and so on. We have a really great feature for exporting PLC configuration for the leading market brands of PLCs, so field bus configurations for integrating the field bus of the device into the PLC. And we have a very flexible I/O system with conveyor tracking. You can really precisely time the I/Os, results, or image triggerings, or illumination triggerings thanks to this. So I talked a lot about AI, and now I want to more get into details of this. So if you want to know what AI is properly in machine vision, then you need to think about what is not AI. So historically, we work with what we call rule-based machine vision, or just classical machine vision. And you can see here in the slide here how there are some tools up here on the side that defines edges and things like this, and then some angles and distance measurements. And then as an engineer, if I know what my part looks like, I can define what kind of distance do I expect here, what kind of angle do I want here, and so on. So it's rule-based. I define rules as an engineer for how the camera system should interpret the images. So what is AI then? Well, to taking a step back a little bit, if you look at what AI actually is, machine learning is considered a smaller part of AI, and deep learning is what we actually, it's an even smaller part of AI. But when people say AI, they're usually referring to deep learning. So deep learning is what we built into this camera, and it's the most advanced AI that happened in the last 10, 20 years, I could say. So what did this do originally in academia? So typically we looked at this kind of problems that was things like, okay, so how do you distinguish cats from dogs? It's very difficult to describe a rule for this. I could say maybe the tail is different or something like this, but how do I, from describing contrasts and lines, tell the camera where the tail is? This is basically impossible. So how is this relevant for industry? So as an example, we have this application of sorting pastas into boxes and making sure the correct box is filled with the correct pasta. And looking at these pasta windows, you can maybe imagine some kind of statistics for what the image looked like that I could describe as an engineer, but it is quite difficult. And if we add more kinds of pasta, it basically becomes completely impossible at some point to do this manually. And this is where we can really use AI inspection. So what I talked about now mainly was what we call AI classification. And that means that you have some examples, maybe a few different products, or maybe examples of different defects of a product. And then you teach the camera, the AI software, to distinguish between these different classes. And then the AI software learns that if it looks like this, then it's an apple. If it looks like this, then it's a strawberry. Or maybe if it looks like this, it's this kind of defect. Or if it looks like this, it is actually okay. What we work a lot with here, that we think is really powerful technology, is anomaly detection. And instead, in anomaly detection, we simply show the camera and we teach the AI software what is a good product. So we can show many examples of what a good product is. And then the camera learns, okay, so this is the normal variation I can expect from a good product. And this means that then when the camera looks at product coming on a conveyor belt, it can, for example, say that it's a defect product, like the worm in the apple here, or maybe this is not the same product at all. But it's important to notice that here we actually don't need really examples of what kind of defects we expect. We can simply say to the camera, here is what a good part is. Tell us when something is wrong. To give an example of how this can work in reality, here is an example of the injection molding application, where you see that this is what we taught the camera, this is what the part should look like, and then all of a sudden in production, it looked like this. And the camera sees that something is wrong here. The camera doesn't know exactly what is wrong, but something is not what we thought it should look like. From this, I want to move into a very, very short demo. So I'm going to show you running live on one of these cameras. It's connected to my computer, so it's lying in front of me. And it looks like this. I'm going to go to the first one here. So this is actually a battery cell like this. I'm going to show you my, yeah, this looks good. So in this battery cell, you can see that there can be some issues. And here you see there's a scratch. There can also be dents and so on. And first here I have an example of a rule-based tool. So this object locator, even though it's actually taught from image data, it's not really using AI technology. It's just trying to find a shape that fits compared to the template that it learned. So now we go through the batteries. You can see that it's essentially measuring the exact position of the battery. And sometimes this is useful in itself, and sometimes this is useful just so that you know where you should look for defects, for example. So if I want to actually inspect these aspects, you see there's a dent here. You see there's a dent here and so on. Then I can, for example, add a AI anomaly detection tool. So now you can see that I have this anomaly detection tool. You see here on the right side, let me introduce this user interface a little bit. On the left side, you see I have different kind of settings. I have my object locator I talked before about, my AI tool here. I can add more tools. For example, if I want to add an OCR tool or a code reading tool, I can easily do that here. But I can also do, for example, communication with Fieldbus and so on. But now you see I'm looking at the inside of the battery here. And you can see here in the middle, there is this scratch. And the camera doesn't really know what is wrong, but it knows something is wrong because I taught it from all these images. You see here on the right side, I gave it some images of what is a good battery and some images of what is a bad battery. And I tell it to look at this inside area in the middle. And if I look closer here, you can see a little bit more in detail what the images actually look like. And it learns from looking at this handful of images. You see it got 11 good images. Then it learns what is a good battery. And then we have 3 images just to help a little bit to set the sensitivity, because that's the thing that is left. The camera knows what a good battery looks like, but it does not know what the sensitivity should be. How good or bad is a battery allowed to be before it needs to be rejected. So that I can do here in evaluation. I see I have taught my system from this basic training data, all happening directly on the device. And now I just need to set the sensitivity a bit. Here, if I had the wrong sensitivity, I could see in the evaluation that my results were not correct. But I just click the auto threshold, and the system has learned that this is the correct sensitivity for my data. I click confirm, and now I can just run the system as it is directly, and it will inspect batteries for defects or not defects. You see there's a different defect here. Some batteries also have an issue with the foil on the side, so I have a separate inspection for that. I call it edge inspection. So in this case, I use the same tool, but here you can see there is an issue with the foil, and this was completely correctly found by this AI anomaly detection tool. So it's just learning from the images. We don't need to describe what kind of defects to expect on the foil. We just say that if the foil doesn't look like the example images, then something is wrong and you need to flag an error here. I can also show that we can combine all these into one big inspection. Then we can simultaneously monitor for issues in the foil or in issues in the middle. And then we have different inspection results here for the 2 inspections. And then we can go here in communication, for example, and send this information out over, say, Profinet or the Net IP, or just TCP/IP connections or digital IOs, and separate all this information or send statistics to another unit on the factory network. With this, I have showed what I wanted to show with this device. I hope that you learned a lot, and I will switch briefly back to the presentation. Another application in battery that we have worked a bit with is this battery recycling. So here we also use, for example, AI inspection to determine the type of the screws used. We can determine damage either through geometrical measurements or through anomaly detection. We use color to determine if it's rusty or not, and we can use this kind of object locator like you saw before to determine the positions of screws to really precisely find exactly where are the screws, and maybe even guide a screwdriver for that. What I showed you now was this very device. I also brought this one with me because you can see there is many different devices here. And the reason for that is that different devices fit for different use cases. Maybe you need a very small device, maybe you need a very powerful device. But all of them are compatible. All of them are using the same SICK Nova software with the same AI algorithms inside. And they all give you all these features that I've shown you. We also have this, what we call the SIM device, the sensor integration machine. And this is kind of a computation box that lets you link to a streaming camera to capture the 2D images here and process them directly. Next up, I just want to give you a brief overview of all the different devices we have. You see they have varying resolutions, everything from 1 megapixel up to 12 megapixels, varying performances and so on, color in some of them. But there is one thing missing, and that is 3D, right? And SICK is supposed to be very good with 3D. Well, fear not, because I have someone who's taking over now and will handle exactly this topic. I'm very happy to hand over the control here to Sofia Nilsson, my dear colleague, and yes. Thank you so much.
Thank you, Victor. So hi, my name is Sofia Nilsson, and I am product manager for this camera, the Ruler 3000. I will spend this session to talk about configurable 3D vision. And I will also talk about a new exciting feature we have that we call Surface Plus. So, SICK Nova configurable 3D machine vision with the Ruler 3000. So Nova that you have seen now, that is also possible to use with Ruler 3000 since about a week. We have this really recently launched. But I will start with a short overview of the Ruler 3000 camera. So Ruler 3000 is our latest camera family within laser triangulation. Ruler 3000 is a unique camera family featuring 6 tailor-made CMOS sensors with ROC technology. It will let you run in an unmatched speed and at the same time deliver accurate measurements down to less than a micrometer. It gives you not only 3D data at high speeds, but also intensity and scatter images. You can run in speeds up to 46 kilohertz, and the high light sensitivity of the sensor let you inspect also very dark materials such as rubber. We have now 15 different variants of the Ruler 3000 with different field of use, red and blue laser options, as well as laser class 2 and class 3R. Previously, the Ruler 3000 camera has mainly been sold to customers with programming skills that write their own software in C++, C#, or maybe third-party software like Halcon. But we have had big demands on making this camera available for everyone, so someone that doesn't have programming skills also can use it. And that is why we are now launching Nova 3D. So this is our new launch since last week, that you can now connect the Ruler 3000 to hardware, a SIM 2000. That of course has a processing unit that runs the image processing here. And SICK Nova, as you have seen here by Victor, is our software foundation for configure machine vision. And we have had it for 2D for some years, and now we're also adding 3D to this. So making high-end machine vision available for anyone, that's what Nova 3D with Ruler 3000 does. It is very easy to use, and that has also been the main focus when we have been developing Nova 3D. it should be possible to use for anyone without programming skills. But still, you get the high performance of the Ruler 3000, and you can run in unmatched speed. It's of course based off laser triangulation technology. That's what the Ruler 3000 camera gives you. It is also possible to customize your solution if you don't find the tool you need. You can easily make a plugin. And the SIM hardware, it has of course a processing unit, and it also has integrated field bus support for both Ethernet IP and Profinet, as well as digital IOs. And I will soon show you a demo, but here is a quick overview of what the user interface looks like. You have already said it in Victor's demo previously, and you will soon see how you can use those 3D tools. But before that demo, I also want to talk about a new patented feature that we have developed that we call Surface Plus for applications that needs both 2D and 3D. So this is a new surface inspection concept enabling simultaneously 2D and 3D inspection. And what you do is that you add an external lighting to your Ruler 3000 or Ranger 3 camera, and you put the lighting just where the laser line is. And this will give you, of course, the great 3D image, but also a very nice 2D image that can reveal dents, scratches, gloss and surface finish variations, etc. In a traditional solution, you would need to have 2 cameras to get those images. And one of the drawbacks of using 2 cameras, as you can see here, is that the images are not aligned. In our solution, the images are perfectly aligned in the same coordinate system. And depending on what defect you are looking for, you choose your lighting accordingly. So here we can see some examples. If you want to find scratches, dark field is optimized to see those scratches. A specular setup will allow for gloss defect detection. Or if you want to see all of this, a compromise would be to have a more diffuse lighting setup. And here you can see some examples. On the top left here, we have a battery cover that is very shiny metal, where you can see scratches very clearly. We have another battery here covered in blue foil, where you can see a fingerprint. We have a steel rod with a scratch, and this is a ceramic tile with a small dent in it. So here is one example setup. We used the Ruler 3000 camera and a LED light to scan this blue battery covered with blue foil. And in the Surface Plus image, we can very clearly see a deviating feature here in the surface. In the photo, you can hardly see it here. We can see a fingerprint as well as a scratch. I also thought I should show you this in a live data. So here we have this data. And as you can see, you have the 3D nice and neat. You can see the foil wrapping very clearly. And on top of the 3D, we have this 2D image where this surface defect is very clearly seen. We have rubbed it with the sandpaper here, and that can be seen very clear, as well as the fingerprint and this tiny scratch. So this is a great feature that is unique for SICK. Next. I would like to show you a short demo of Nova 3D. So how to use Nova 3D with Ruler 3000 images. And I want to show an example of where I have scanned this battery. And I want to show how to measure the height of the poles, measure the coplanarity of the poles, as well as the distance between the poles. Also on this battery, you can see that we have a data matrix code that is a bit shiny. It's a bit hard to see also even with the eye. But here I also did this Surface Plus setup, added this external lighting to get a very nice image also of this data matrix code. So let's have a look. So here we have Nova 3D. And here we have the image of this battery that I have scanned. If we look at the intensity data, we can see that this data matrix code is hard to see. But looking at the Surface Plus image, we can easily see this data matrix code, and it will be possible to read it. In this first release of Nova 3D, we only have 3D tools available. But after summer, we will release also the possibility to use 2D tools on the 2D images from the ruler. And by then, you will be able to read this data matrix code also. But for now, I will show how you do the 3D measurements. So I have the tool list here to my left, and I will highlight the overlay graphic for each tool as I talk about. So first we have an object locator just to localize the battery. And as you see, we have a 3D region here, and it's very easy to just edit the 3D region in the viewer. So I localize this part of the battery to recognize the battery in each image. Secondly, I want to find, or I want to fit a background plane to the main part of this battery lid, so that I can measure the distance from this plane to the top of the poles. So let's see here if I get it to show. Some reason it doesn't show this. Let me reload the page here to see. I can. Here we go. I go back to my Surface Plus image. So here I have you can see that I have a background plane. That's the blue area you can see here. That is the background of this lid, basically. So once I have this plane, I want to find the battery poles on top of this plane and measure the heights of them. So I use a blob finder tool, and you can see that the output here is the 2 poles that are marked blue here. And I get a list with the information of those blobs, and I can here get the height of the poles. And those values can easily be sent over Ethernet IP, TCP IP, etc. To a PLC, for example. So I have found the poles, and secondly, I want to fit a plane to each of the poles, and I want to measure the coplanarity of those 2 planes. So here I have fitted a plane to each pole, and I add an angle tool where I can choose what features I want to compare. So I have chosen my plane for pole 1 and my plane for pole 2. And I get the angle that is 0.1 degree between those 2 planes. Of course, I can also specify a tolerance here. And if the angle exceeds the tolerance, the tool will fail. Yes, and finally, I want to measure also the distance between those 2 poles. So I use an edge fitter for each side. So zooming in here, we can see here that it finds this blue line that is the edge of the first pole. And it finds another blue line here that is the edge of the second pole. And here we have a distance tool that takes 2 inputs. So I can take the verge edge, the center of the verge edge, for example, and the center of the second edge, and measure the distance between those 2 edges. And the distance is 97.1 millimeter. Of course, I can also specify tolerances here that will make the tool fail if it's not the correct distance. So I hope I managed to show you with this how easy it is to use Nova 3D and how we can make high-end machine vision available for anyone. And actually, there is more options to get very nice 2D images from our 3D streaming cameras. Surface Plus is one option, but we do have another option that my colleague Nils will talk about. Let's see here. And I will turn camera on. And Nils, sorry. So here we go. Welcome, Nils, to talk about Ranger 3.
Thank you. Hello, everyone. I'm the product manager of our Ranger 3 camera. The Ranger 3 is our most high-end 3D streaming camera that we have in our portfolio. It's basically a Swiss Army knife to solve a wide range of applications, from inspections in the electronics industry on micrometer level up to scanning whole train sets passing by in over 100 kilometers per hour. So with this camera, the user chooses the lens, the laser module, and the geometry to create the optimal setup for their specific applications to get the optimal results. And today I will, as Sofia said, talk a little bit about the next step after Surface Plus on how to yet another technology on how to capture 3D and 2D at the same time. So this is a very unique and market-leading technology that allows us to capture more data with the same camera at the same time. So in the battery industry, we are quite often challenged with demanding inspection tasks. And often we need to add an extra 2D camera to the 3D camera to solve the applications. This makes the solution more complex. It requires more engineering work. It requires more integration work. And basically, it's a more expensive solution. So let me show you some examples. So in this case, we have an aluminum case for a battery cell. In this case, we want to, of course, look at the surface of this case to make sure that we don't have any scratches. We want to look for dents so that we don't have any too deep dents in the surface. Maybe we also want to look for contaminations like dust or other contaminations like glue rests or something like that. And typically we also want to verify that the surface is flat, that dimensions of the case is correct, maybe that the edges of the case is not damaged, and that it's like not squeezed together so that the contents will fit into the case when times come to put in the contents into it. Typical 3D scanning tasks. So we can scan this in 3D. We get a height map image that looks something like this. We can clearly see that we have height variations in the surface. We have different heights that is indicated by the different colors. We can measure the difference between these heights to make sure that they are not too big. We can see some of the deeper dents, and we can just about see actually deep scratch as well. But seeing finer dents and especially finer scratches is basically impossible in 3D because there's just not enough. The scratches are not deep enough to see it, even though we have a very high resolution camera. So we need to add a 2D camera, and then we also need to add a light and set that up in a very clever way so that we enhance the scratches in the surface. And then we will get an image like this, where we clearly see all the scratches in the surface of the material that we scan. Setting up the light in another way, we can also scan it with a 2D camera and reveal all the bumps in the surface, and then we get an image that looks like this. And here we clearly see all the bumps. We even see the very small dents in the surface appears very clearly in this image that is basically not detectable by the human eye. Combining these two together, we get an image like this. We can take this image and then we can send it into a deep learning network to look for anomalies on the surface. When we get this back, maybe the network has found some anomalies for us, and we can then go back into the 3D data, and then we can actually measure how big are these dents that we have found, or that network found for us. And then we can decide, is this a reject, or is it something that will go on in production? So to solve this application, we basically need a 3D camera to do some measurements, and we need a 2D camera to see scratches and dents and possibly dust particles and stuff like that it's hard to detect in the 3D camera. In this next example, we have a top of a finished battery cell that we have scanned in 3D. This might be a inspection in end of line of production, for example. So looking in the 3D data, we can look for certain details. For example, we can see that the corners of the protection of the top of the battery cell has not sticked properly to the top of the cell. So here we have two defects. We can also make sure that the protective caps are mounted on the poles of the battery, and that they are mounted correctly, so we can measure the coplanarity of the surface of the battery cell and the top of the protective caps. And in this case, we can see that this cap is not mounted correctly because the plane is tilted a bit. So typical 3D tasks. But maybe we also want to make sure that the QR code is there, the serial number is there. And when we scan this with a normal 3D camera, a laser triangulation camera, we get our height map that we see now, but we also get an intensity image, what we see here basically, and that is the intensity of the laser line that we look at. But in those images, it can be very hard to see details like QR codes, numbers, and letters and stuff like that, because we always want to optimize the exposure for getting good 3D data and not getting good intensity data out of the camera. So we can verify that the QR code is there maybe, but we can't read it in scan data from the normal 3D camera. So here we also need to add a 2D camera to be able to get good 2D data, to be able to read the QR code and read the serial number. Maybe we want to store that in our database to make a log of what we have, what cells we have scanned that leaves the factory. Finally, we might also want to check that the protective caps on the poles are of the right color, so that we haven't mixed up maybe someone poured red caps in the black container, so we have reversed the polarity of the protective caps, and the end customer will be confused when mounting the battery. So this we also need to have a color 2D camera to do. So even also in this example, we see that we need to have a 3D camera to do some measurements, and we need a 2D camera to do other measurements. And imagine if we could do all these inspections from these two examples with one and the same camera in one single scan. And this you will soon be able to do. So we will soon launch a new Ranger 3 variant, where we are building in high resolution color line scan functionality into the Ranger 3 camera. So this will make it possible to capture high quality 3D data and at the same time capture high resolution RGB and grayscale 2D data. So basically we will have two different imaging systems on the same imager chip. So we will have the normal 3D scanning on one part of the imager that has 2560 pixels in resolution in width. And then we will also have a part on the sensor that has 4 high-resolution lines with 5120 pixels each. So there will be one line for red, one line for green, and one for blue, and one for grayscale. And those two systems are independent of each other, so we can capture data from both of them at the same time. On top of this, we are also extending the network interface from the 1 gigabit interface that we have today to a 2.5 gigabit interface to be able to push the added high-resolution data to the PC side at full production speeds. So, as you probably have guessed, all the images in those two examples I showed you are, of course, captured with the new Ranger 3 camera in one scan. So, with one scan, we can capture all the data we need to solve these two applications. So this camera will be launched after summer. So let's look a little bit more into the new high-speed network interface that we're adding as well. So the new network interface will significantly raise the number of profiles per second that we can scan our objects in. So basically, we have been limited by the 1 gigabit interface we have today on the camera. So with the 1 gigabit interface, we can reach a max profile rate on 46,000 3D profiles per second. But then we have to narrow down a little bit the width, how many columns we use on the sensor. So using the full width of the sensor, we can scan in 31 kilohertz. But with this new 2.5 gigabit interface, we are significantly raising the amount of data we can push from the camera to the PC side. And this means we can also run the camera a lot faster than we can today. So we will be able to run the camera at 69 kilohertz using the full width of the sensor. So this, of course, allows you to scan that the objects you are scanning are moving much faster, or that you can scan your objects much denser, taking more profiles. Yes, and if you're using the high-res color functionality, we will be able to scan in 15 kilohertz, and if we only use the gray component in the high-resolution lines, we can scan at 30 kilohertz. So, to sum up a little bit, we will launch a new Ranger 3 variant to the product family range. It will have 2 imaging systems on the same camera. This will make it possible for you to solve more inspection tasks more accurately with just using one single camera. It will also have a new 2.5 gigabit high-speed network interface that will make it more than twice as fast compared to the current Ranger 3 that we have today. And this camera will be launched during autumn in 2024, so it will come very soon. And with those words, that was all for me. So it's time to sum up a little bit. And if you have any questions, we'll be happy to answer them.
Okay, great. So should we look into the summary slide, Håkan?
Sorry.
Yes. Okay, thanks for listening in so far. We hope you enjoyed it. The key takeaways we would like you to bring from this is that with us at SICK, you will find a large scalable product portfolio with lots of vision offerings. To go with that, we are a big, competent team giving technical support worldwide. There are local technical support teams in each country, and we in Linköping serve as second line for this. Secondly, stay tuned for more exciting new launches, specifically the 3 that Victor, Sophia, and Nils was talking about. Inspector 830 coming out as the new standard for AI-based solutions. Nova 3D. Solving 3D inspection applications have never been easier. And Ranger 3 high-speed color, the Swiss Army knife for advanced applications. To help you out finding more information, you can dial into SICK.com, of course, but you can also visit us at the battery show in Europe coming up in June. So if you scan the QR code here, that will direct you to a page where you can register and get a free entrance ticket. So go right ahead with that. And with that, we thank you for your attention. And we now shift to the Q&A session. Sorry.
Good.
So if you have any questions, fire them in the chat, and we are happy to respond.
Thank you, Håkan. I think that it's questions incoming here. One I think is to you, Victor, regards AI tool. Can you run more than one tool at the same time and combine the powers of all tools?
Yes, the tools you saw, I mean, I showed the object locator and the AI anomaly detection, but you saw in the list, there was a lot of tools, and you can actually kind of combine them in any way you want. You can, for example, run classification at the same time as anomaly detection, or you could do some distance measurement at the same time as the AI tools, maybe if you want to log some measurements or something like this. So you can really kind of combine in any way you want, I would say. It's very flexible.
Good, good. Let's see, here's another one. Should we take this? AI tools for 3D, Nova 3D. What is the plan?
Well, we plan that after summer, we will launch the possibility to use 2D tools in Nova 3D. And that means that all the existing AI tools for the 2D images will be available. So you could use those tools on the nice Surface Plus images you saw, for example. So yeah, within autumn.
Do we have any launch date for Nova 3D?
Yes, it's already launched. So it was launched last week, Nova 3D. This first version containing the 3D tools. So you can find it on SICK.com.
Great, fantastic. We have a question here also regarding Ranger 3. So how do you avoid light source crosstalk when using multiple illuminations?
Yes. So there's basically 2 independent imaging systems that I mentioned. So we can delay the exposure of these 2 systems so that we can basically turn on the laser only when we capture the 3D data, and then we turn off the laser till we capture the 2D data and turn on the LED light, so that the laser and the LED light is only on when we capture the 3D or the 2D data. So they will not be on at the same time, basically. And I can also add one thing that I forgot to mention is that you can, of course, also capture Surface Plus data with the Ranger 3 at the same time as you capture high-resolution data with the high-resolution lines.
Great, great.
Not only that, actually, because if you have a color camera with red, green, and blue light, you can use green light, you can use red light and blue light. And then you can have these light sources on simultaneously and have only the wanted light filtered off by these red, green, and blue color lines as well. So that's actually another option.
And that's how we solved the first example app with only one scan, actually.
Okay, great. Thanks all the team, and thanks to all of you that have been listening. I think the time is out, and we will answer additional questions via email or other sources. So many thanks for joining the Battery webinar, and hope to see you. Okay.
Thank you very much. Have a very nice day. See you around.
Thank you.
Bye-bye.